Hi Fiona, Craig and Daniel. So we had a week off last week. I hope your presentations all went well. The week before we were doing sorting and now we're doing searching. And often people think about these two algorithms at the same time because they use the same sorts of techniques. So searching is an action which is now taken for granted by users of computer systems. I'm sure you often search for files or names or emails on your system. It's something you do all the time. So we often search for saved content to call or even to send an SMS to on a phone, and that obviously, while it's not being a traditional computer, it's got a computer chip in it and uses the same algorithms. We search for messages in our inbox and we search information on Google, and all these things are different ways that we search for things. Even typing the URL to a website fires some search behind the scenes. At the very least, actually a DNS search is done to determine the website's IP address. So in many ways, searching is behind lots of the things that we do all the time with computers. Searching can be quite an arduous process. Try, for example, searching for a particular string of text in a book without using the index, and you'll realise how difficult it really can be. For this reason, a number of search, and later today we'll look at pattern matching algorithms, have been developed. In this lesson, we're just going to go through two of them, linear search and binary search, and we'll also talk a little bit about the brute force method. So linear search involves going through every piece of data, checking each one to see if it matches what we're looking for. For example, assuming that we're searching number 41 in the array below, we'd compare the key with every single element in the array in a linear fashion until we found a match. On finding a match, we can return the position of the array, or if it wasn't found, then we return -1. So let's assume that we have an array containing n elements. A linear search goes through and compares every element with the search key until a match is found. In a worst case scenario, every element will be checked and then we'll say that it wasn't in that array, in which case we return a -1. Which means the worst case complexity is big O of n, which is not great. It's the length of all the data. So we want to improve on that, and the way we tend to improve on that is by using a binary search. We can improve the performance of the linear search by sorting the array, and then we have to perform a binary search. So remember, in order for binary search to work, the array has to be sorted. So let's sort the array we saw previously, and then we get the following. To search it for 41, we simply check the number in the middle of the array. If it's what we're searching for, great, we're finished. Otherwise, if it's less than 41, then we discard all the numbers to the left, or if it's greater than 41, discard all the numbers to the right. We continue until we are left with one element. And if that's not the element we want, we can safely say the element is not contained in the array. You might notice this type of algorithms. We've seen this before when we did sorting. This is a divide and conquer algorithm, exactly in the same way as quicksort was. So let's see an actual example. So every time we do a comparison, the array size is halved, hence the term binary search. The first thing we have to do is obtain the middle index. We add the leftmost index available and the rightmost index and divide by 2. If it's an odd number, you can either discard the fractional part or you can round up. It doesn't really matter. We'll discard the fractional parts. I think that's what most people do on purpose, but it doesn't make a lot of difference. Okay, let's actually see how we do this for this array. So the lowest index we've got in this array that we're searching in is 0. Remember, that's because we're searching the whole array. We might be searching a part of the array and then we'd use the lowest index that we're actually searching through. So we're going from 0 to the highest number here, which is 9. Divided by 2 gives us 4.5. We're going to discard the fraction and round down and make that 4. Therefore, we search at index 4. We find that in index 4 we've got the number 39. Since 39 is less than the 41 we're looking for, we discard all the numbers to the left. We then, and this is really important, we then repeat the algorithms. We do our divide and conquer again. So now we're going from index 5 to index 9. Divide that by 2 equals 7, so we start at index 7, we get 58. 41 is less than 58, therefore we discard everything greater than 58, so 58 to the right onwards. That leaves us with two numbers left, 41 and 52. We do our comparison again to find the middle of just that two arrays. We get 5 to round down, and alas, we find our number. So as opposed to scanning through the whole data, we found it on our third attempt. So time complexity of binary search: for each comparison, the length of the array is halved. Therefore, any array of the length n, we have a maximum of operations equal to log n. Remember, whenever we say log n in computing, it's to the base 2. Therefore, the worst complexity of binary search is big O log n. This is much faster than linear search, but the linear search required 10 comparisons, the binary search required just 3. However, remember that we needed the data sorted. So if the data was unsorted, also did sorting, then it becomes a bit more difficult to see which one is going to become more effective. And that, what is more effective, is going to be exactly what you do today. So I'm going to ask you to do the sorting algorithms from last time to compare linear sort and binary sort, having implemented your own linear sort.